lesson 3.2, linear functions. You should be on page 112. You will learn in this lesson how to identify linear functions using graphs, tables, and equations, how to graph linear functions using discrete and continuous data, and how to write real-life problems to fit data. So let's talk about a linear function. You might remember the last lesson was just on functions. This lesson is specifically on linear functions. So we need to know, what does linear mean? A linear equation in two variables, x and y, is an equation that can be written in this form, y equals mx plus b. Some of you might recognize that form already, where m and b are constants. Guess I don't know if I totally agree with the book with this. B would be a constant. M would be, remember, a coefficient. Coefficient is a number in front of a variable. Okay. The graph of a linear equation is a line. Look at the word linear. Can you see the word line? Okay. So any linear equation or function would always give you a graph that's a line. A linear function is a function whose graph is a non-vertical line. Now, non-vertical means any line that's not completely vertical would be a linear function graph. So the only time a line is not a linear function is if it's a complete up and down line. A linear function has a constant rate of change and can be represented by a linear equation in two variables. So all linear functions can be written in this form, is what that's saying. And if you look at a table, if the table has a constant rate of change, it would be a linear function. Now think about it. If linear means line, a nonlinear function would not be a line. It would be some other, like a curved graph or something that's not a straight line. Nonlinear functions also do not have a constant rate of change. Okay, you notice that does not have a constant rate of change. Let's take a look at these samples. Like in part A, does the graph represent a linear or nonlinear function? Well, this is certainly nonlinear. It's not a line. And part B, this is certainly linear. It is a line. Pretty easy. Should be really easy for you to look at a graph and determine if it's linear or nonlinear. Actually, looking at tables should be easy too. Let's start with this table. Is this linear or nonlinear? We'll look below. You notice how x is always increasing by 3, but y is always decreasing by 6. The rate of change is the same. It's constant. That means this is a linear table. Okay? Constant rate of change means linear. Let's look over here now. This table. As x increases by 2, do you notice how the amount y increases by is changing every time? This is not a constant rate of change. This is not linear. This is a nonlinear table. Should be very easy for you to look at a graph or a table and determine if it's linear or nonlinear. I'd like you to quickly pause and try these four. Determine if these graphs or tables are linear or nonlinear. Okay, you've had a chance to do that. This is certainly a line. This is linear. That's not a line. It's nonlinear. Here, this table is linear. X goes up 1 at a time. Y goes up 2 at a time. That's constant pattern. That's linear. Here, X goes up 1 at a time, but look at Y. It goes down 8. Then it goes down 4, then it goes down 2. That's not constant, that's nonlinear. You should also be able to look at an equation and determine if it's linear or not, and that's pretty easy to do too. Something the book doesn't talk about that I want to teach you right now, this is how I think it's the easiest way to tell if a equation or a function is linear or not. Linear equations are always first power with variables in the numerator. Okay? Now numerator means, of course, top of the fraction. So when you look at these, like this equation here, it's variable first power, and in numerator it'd be in the top of the fraction. This is definitely a function. That equation would be a function. This equation is not a function. Radicals are not first power. So it's breaking this rule. So this is not a function. This is not first power. This is x power. That's not a function. You notice how I have a variable in the denominator. I need to have an equation with all my variables in the numerator. That's not linear. Now this, that's definitely that's definitely linear. I have variables both in numerator, both first power. That's definitely a function. And you notice here, I have a variable to the second power. That's not following this rule. That's not a function. I think that's the easiest way to do it. Just look. So go down here, you pause the video, you try these three. It only should take you a few seconds to determine, based on what I put here, if these are functions or not. Okay, I'm back. Here, both my variables are in the numerator. They're both first power. That's definitely a function. Here, this, both variables first power. This is numerator. Definitely linear function. Here, you notice second power. That's not linear. That would be nonlinear. Okay? This is going to give me a curved graph. These two will give me straight line graphs. Let's talk about how we can represent a function. When you read the words, an output is 3 more than an input, that should be easy to write an equation for. Now think about it. Didn't we learn in the last lesson, outputs are y's and inputs are x's? So when I read this statement, here's what I'm thinking. Y is 3 more than x. Okay? Y is means equals. How do you write 3 more then? That means add 3 onto something. I'm adding 3 onto x, so you can see that right here. Okay? Now there's 3 ways I can write this function. I could write it in table format. I could put values in for x, which will give me outputs for y. I could write it as a mapping diagram, or I could graph this data. I could have the data displayed in 3 ways. Table, mapping diagram, or graphing. You might want to write that down in your notes. You can represent a function by table, mapping diagram, or graph. In fact, you might want to pause the video and write those 3 things down. Let's talk about graphing linear functions. A solution of a linear equation in 2 variables is an ordered pair that makes the equation true. For example, let's just pick something easy. Y equals x plus 1. Does it make sense if I put a 1 in for x and a 2 in for y? That would make this statement true. That would be a solution, the ordered pair 1, 2. The graph of a linear equation in 2 variables is the set of points, x, y, in the coordinate plane that represent all solutions of the equation. So think about this. Is this the only answer to that? And I hope you're thinking, well, no, I could put a 2 in for x and y could be a 3 and that would be an answer. You know, I could put a 3 in for x and get 4 for y. In fact, there's a whole bunch of correct answers I could have here. Okay? That's one of the reasons why we graph these, because if I told you, go home tonight and write down all the ordered pairs that make this true, I hope you're thinking, I would never get that done. You can't. It has infinitely many correct answers. So again, graphing is often the shortcut. That's why we often graph our solutions. Now, when we graph, sometimes the points are distinct, and other times the points are connected, which gets us to what we call discrete and continuous domains. Now remember, domains are x values. A discrete domain is the set of input values, that's x's again, that's a set of x's that consist of only certain numbers. Like here would be an example of a discrete domain right here. If I wanted the integers from 1 to 5, that's specific numbers. That would be 1, 2, 3, 4, 5. That would be individual points being graphed. That's discrete, individual certain points. Continuous is something different. Continuous is a set of input values. Remember, input's x's. It's a set of x's that consist of all numbers in an interval. That's different than what I just said here, because if I want all the numbers from 1 to 5, that graph would look different than what's up here, because I could have 1.1, or I could have 2.01, or 3.99. I'm looking for all the numbers from 1 to 5. Okay? This down here would be a sample of a continuous graph, where up here is an example of a discrete graph. Let's talk about graphing discrete data, that's select data. The linear function y equals 15.95x represents the cost, y in dollars, of x tickets for a museum. So think about that. Y is the cost. Y is the cost of the tickets. Each ticket must cost $15.95, and x is the number of tickets I could buy. Okay, so next, find the domain of the function. Is the domain discrete or continuous? Let's think. I could buy 0 tickets, 1, 2, 3, or 4. That's select numbers. That means this function is definitely discrete. Okay? So they're going to make a table here. Here are the inputs. You could plug in 0, 1, 2, 3, 4. The outputs. So if I take 0 and multiply it by 15.95, my output would be 0. If I buy 1 ticket, it's going to cost me $15.95. If I buy 2 tickets, it's going to cost me $31.90. If I buy 3 tickets, I multiply that by $15.95. There's my price, and 4 tickets, so on. So you can see I have the ordered pairs 0, 0, 1 and 15.95, 2 and 31.9, 3 and 47.85, and 4 and 63.8. I need to take those points and then just plot them on graph paper, which you see they're doing here. There would be a graph of my data. Now, do you notice, when you make a graph of real-life data, this graph has a title. This graph has both the y-axis and x-axis labeled. Those are all important things to do when you're making a graph of real-life data. I would like you to try this problem. Read it, find the domain of the function, answer if it's discrete or continuous, and then graph that function using that domain. Okay, I'm back. So first of all, we want to find the domain of the function. Is the domain discrete or continuous? Explain. Well, first of all, I have $50 to spend, and since each DVD is obviously $9, I could buy at most 5 DVDs, because if I bought 6, I ran out of money. I only have $50. So here would be a table. If I buy no DVDs, I have $50 left. 1 DVD, I'd still have $41. 2 DVDs, I would still have $32 left, and so on. This is definitely discrete. It's select values for my domain. Like, I can't buy 1.5 DVDs. Okay? Let's graph the function using this domain. So I'm going to take this data and graph it. So I made a title to my graph, money remaining after DVD purchase. My y-axis would be the amount of money I have left, and you can see my scale. My x-axis is the DVDs I purchased, and all I did is plotted those points in my table. I took this table right here, and I'm plotting these individual points. Now, if I graph continuous data, it's going to be the same process, other than my graph won't be individual points. It will end up being me taking my ruler and connecting those points with a segment, line, or ray. So here we have a cereal bar contains 130 calories. The number C of calories consumed is a function of the number of bars eaten, B. So think about that. I could eat, let me write out a little table here, B and C. If I eat no bars, I ate no calories. But if I eat one bar, this says I eat 130 calories. If I eat 2 bars, I would have 260 calories. 3 bars would be 390, and so on. But here's the question, could I eat a half a bar? If I ate a half a bar, would I eat half those calories? And I think you're saying, sure you would. What if I ate a quarter of a bar or a tenth of a bar? Is it making sense I could eat any fractional amount of bars I want? That means this is definitely a continuous problem. So when I go to graph this, look at what they do. They take the points, they plot them. You can see 0, 0, 1, 130, 2, 260, 3, 390, and so on. But this time they take the ruler and they're drawing a ray through those points to represent all those fractional amounts of bars that I could have eaten as well. What I'd like you to do is pause the video and answer these 2 questions. Okay, I'm back. For this first problem, is this domain discrete or continuous? Well, it's definitely discrete because number of stories of a building. I can't have half a story or 3/4 of a story. It's whole amounts. This is definitely discrete. If I was trying to graph this, I'd have to graph these select amounts. In number 20, a 20-gallon bathtub is draining at a rate of 2.5 gallons per minute. The number G of gallons remaining is a function of the number of minutes. So if I can picture that, I could take the gallons of water minus the drain rate would equal how much is left in the tub. I should put how much water's left, how much H2O is left, okay? So now I got to just fill in the numbers. How many gallons of water are in the tub? Well, it said 20. The drain rate is 2.5 gallons a minute, and G is how much water's left in the tub. So this is definitely linear. Do you notice how each variable is first power and everything is in the numerator? And is this domain discrete and or continuous, and tell what it is? Well, the longest the tub could drain would be 8 minutes, because if I put 8 in here, this would work out to 20 minus 2.5 times 8 is 20. There'd be no water left in the tub, okay? So I could be draining the tub anywhere from 0 to 8 minutes. Now, could you let it drain a half a minute or a quarter minute? Oh, sure. So that means this is a continuous domain. And to finish up the video, writing real-life problems. Write a real-life problem to fit the data shown in each graph. Is the domain of each function discrete or continuous? Explain. Well, I think sometimes for students, I think sometimes you guys overthink this. Let's look at this graph. 0 produces 6, 1 produces 5, 2 produces 4, and so on. What if I said this? You go to 7-Eleven and you have $6 in your pocket. Every big gulp is $1. This graph could show how much money you have left in your pocket after buying X number of big gulps. So for example, if you buy no big gulps, you have $6 left in your pocket. That's where the 0.06 is coming from. Or if you buy 1 big gulp and it costs $1, you got $5 left. Or if you buy 2 big gulps, you would have $4 left. This would definitely be a discrete graph. Like, you can't buy a half a big gulp, okay? Now, this graph, I'm going to change things a little bit. Here's the number of big gulps you purchased, okay? So this is the, you have 6 big gulps purchased, and we'll say X is how many big gulps you've drank, okay? How many you drank. So, if I bought 6 big gulps and I haven't drank any, I still have 6 left. Or let's say I drank 1 of the big gulps, I still have 5 left. Or what if I drank 2, I still have 4 left. Now, Could I drink half a big gulp? Well, sure you could. If you drink half of your 6 big gulps, you'd still have 5 and a half left. Or what if you drank 4 and a half of your big gulps? You'd still have 1 and a half left. This is definitely a continuous situation. So there's writing a real-life example for those. I'm going to stop the video here. If you have questions, make sure you ask in class.